Hello everyone. In this video I am going to show you how to find slope and deflection using method of double integration. And this is the example 2 of this method of double integration video series. So this is the problem. It says the cantilevered beam shown in figure is subjected to a couple moment of 15 kilonewton meters at its end. Determine the maximum slope and displacement at A using equations of elastic curve. EI is constant and beam length is 12 meters. You can see the figure below, and this is the length of 12 meters, and you can see a moment at A 15 kilonewton meters, and you can see X, and it is marked from point P to point A, and this black line is the deflected shape of this cantilever beam. And please keep in mind, this is a cantilevered beam, that means at P it is fixed. So these are the common deflected shapes in different conditions. So I explained this in example 1. I am not going to explain in this video this all conditions. Anyway, in this video we will need only this condition. So it's a fixed support. At fixed support, deflection is equals 0 and slope is equals to 0. So this is the beam, and this black line is the deflected shape of this cantilever beam, and you can see here I marked V, that is the deflection of this beam. If I draw a tangent line at this point, it will go like this. You can see this green straight line. So you can see I marked theta here, that is the slope of point A. So our first task is to find in support reactions. So since we have a fixed support, we usually mark 3 components, which are moment component and 2 force components. So next I am going to find these support reactions. First I will consider sum of all the vertical forces. If I consider vertical forces, you can see there are only one vertical force, which is Py. That means I can write Py equals 0. Next I am going to consider sum of all the horizontal forces. Horizontal forces also, there is a one horizontal force. So therefore I can write Px equals 0. Next I am going to take the moments. Since there are no support reactions, I can take moments at any point of this beam. If I take moments to the counterclockwise direction, I will have 15, which is this moment, minus MP. MP is this moment, and it is clockwise direction. Therefore I put minus sign here. I consider counterclockwise direction. So if I simplify this, I can get MP equals 15 kilonewton meters. So this is the free body diagram. There are no support reaction in this beam, just two moments, which is MP is 15 kilonewton meters, and there is a moment at A of 15 kilonewton meters. Next I will cut this beam through this point. So next I will consider this small part alone. So this is the small part of the beam. So you can see this is the MP, it is 15 kilonewton meters, and this is the new moment of M. Next I am going to find this moment of M. For that I will consider counterclockwise moment of this small part of beam. When I take moments, I can get M equals 15 kilonewton meters. So this is the equation of double integration method. This is an important equation. You have to memorize this equation. Next I will solve this equation for M. So if I get answer for M, you will get this equation. Next I am going to substitute this M equals 15 value to this equation. If I substitute this, I will have this equation, and I will label this equation as equation 1. So E is the material's modulus of elasticity, and I is the beam's moment of inertia computed above the neutral axis. Next I am going to integrate this equation 1. If I integrate this, I will have this equation ei times dv over dx equals 15 times x plus c1. So this is an indefinite integration, therefore I have to put a constant. So I put c1 as the constant, and I will label this equation as equation 2. Then again I will integrate this equation 2. So if I integrate this, I will have eiv equals 15 times x to the power 2 over 2 plus c1x plus c2. Here also I have to put a constant because this is also an indefinite integration, and I will label this equation as equation 3. So here I wrote all three equations for my convenience. In previous example, they ask in finding deflection. So in this example, they are asking finding slope and deflection. So how we find slope using double integration method? So slope is equals to theta equals to dv over dx. So if you closely look at these three equations, in equation 2 you can find dv over dx. So if you find this dv over dx, this is the slope. So we will see how to find slope using double integration method in this video. Next I am going to apply boundary conditions. When x equals 0, which means at point P, it's a fixed support. So at point P, deflection is equals to 0 and also slope is equals to 0. So when x equals 0, dv over dx equals 0, which means slope is equals to 0. So from equation 2, from this equation, I can write ei times dv over dx equals 15x plus c1. This is the equation 2. I can substitute x equals 0 and dv over dx equals 0 to this equation 2. If you substitute dv over dx equals 0 to this equation, this whole part equals to 0. And if you substitute x equals 0, this part becomes 0. Therefore only left is this c1, so it is equals to 0. Next, I will consider x equals 0 and v equals 0. So that is the deflection. So if I substitute these values to the equation 3, I can write. So here also I can get c2 equals 0. In order to find slope at A, we substitute theta equals dv over dx, that is the slope, and c1 equals 0 and x equals 12, because at A x value is 12. This beam length is 12 to equation 2. So this is the equation 2. If I substitute this, I will have ei times theta equals 15 times 12, which is this value, plus 0, which is this value c1. c1 equals to 0. So if I simplify this, I can have 180 over ei. Please keep in mind this is the units. Units are radiant. In order to find displacement at A, we substitute x equals 12, c1 equals 0 and c2 equals 0 to the equation 3. So this is the equation 3. So I can substitute those values. X equals 12 and c1 and c2 both are equals to 0. So if I simplify this, I will have v equals 2160 over 2 times ei, and units are meters. So that's how we find slope and deflection using method of double integration. So let's look at our sign convention. I showed this in example 1. So this is sign convention. Positive values for slope are counterclockwise. So our answer is positive, so it's counterclockwise. So you can see here. So if I mark theta here, I have to mark it like this. So you can say it's counterclockwise direction. So according to our sign convention, it's right, it's plus slope and it's counterclockwise. Then positive displacement is upward, so our displacement is positive value, so you can see this displacement is upward.